So I want to today show you how to derive the moment of inertia of a sphere. So that's that's our goal. I'm not thinking about like a sphere, like a hollow sphere. I'm thinking more of, how we say, solid sphere. Something with a substance inside, so that all of the sphere is filled. So if I was to draw this out on an axis, something like that. Okay. It doesn't matter which way I rotate it, because it's uniform throughout, and the whole sphere is filled. Okay. But we need to look firstly to identify the parts of our sphere. We have a radius that goes out from in the center, something like that, which we'll call ρ for now. And I'll tell you why we call it ρ later. Okay, we're setting up. We have an angle going from the inside out, so that's going to be phi. And we have angle going from that point to the outside, and that will be theta. Okay? And as you'll learn, the moment of inertia is showing us the resistance to rotation of a particular body. Okay? That how hard is it, how difficult it is to rotate is measured by this quantity moment of inertia. Okay? And so, this moment inertia is represented as the sum, or the integral, of the square of the radius distance of this distance r times dm, which is the mass, the change in mass, of course. Okay? And there's a very long explanation. I can derive that equation for you, but I'm lazy and don't want to do it for you today. So, but you can look at another video and we'll go to the derivation of that formula and why it's r squared. But for the purposes of this, we know the integral of r squared dm is the moment of inertia. What does it represent? The sum of the square of the distance times the change in mass. That's what it's representing. Okay? Now, this r here is represented on the radius here, like that, r. And the relationship is represented by this angle phi. And actually, we don't want this radius distance here. We just want a piece of it. We want the component that's along the axis of rotation, which in this case is rotating it around the z-axis. So, that r is represented by the Greek letter ρ, sine of phi. Alright, now, and I leave it unsubscripted for now because we actually use letter ρ to represent density as well, and we'll talk about that in a minute. Okay. So, I know you can't really see the picture here, so I'm going to put a quick picture to the side like that. There's the angle phi. This is ρ, or r. Okay. And so, r divided by ρ, and of course r is equal to ρ sine phi. Okay? So that's how we get it. And then we take that and we plug it in for r squared, here like that. So to show this integral, the integral of rho sine phi squared dm. Everybody follows so far. So we're just looking at the piece of this. And so now, of course, the square, this reduces. So let's show it again. Here, I'm going to go ahead and clear this. If you want to see this again, go back in the video to be able to look at it. Okay. And so we know I is equal to the integral of rho squared sine squared of phi dm. Now, we need a relationship to work with this dm. Almost never do we integrate it with respect to its mass. As you can see, mass is not located anywhere in this integral at all. And we actually have to do two substitutions in order to make this work. Okay? This change in mass is represented, of course, by the density of the sphere. Okay? So this, my little picture way up here in the corner, has a density rho sub s, we'll call it rho sub s, is equal to m divided by v. Or, another way of representing it, dm is equal to the density of the sphere times the change in volume. So we're going to change this mass into the relationship with its density. Okay? So you don't get confused, I wrote rho sub s for density of the sphere, density of the entire sphere. So this integral, integral of rho squared sine squared of phi dm becomes density of the sphere times dv. Okay? Times the change in volume. What's the change there? So density of the entire sphere, its mass with respect to its volume. How do we determine the mass of a sphere? Take the density of it, multiply it by the volume of it. Doesn't matter what that density is. Now, for that change in volume, okay, we're working here. Volume is, of course, in 3 dimensions. And because it is in 3 dimensions, we have a special relationship to it. Okay? We're going to use the spherical coordinate relationship here. We're going to use the spherical coordinate relationship and make it into a nice pretty triple integral instead of this hideous ugly integral with 1 in it. So dv is related by rho squared sine of phi d rho d phi d theta. Okay. What that represents. Okay. The volume represented by, of course, the square of the radius here. This rho is the same as that rho, not the same as density of the sphere. This rho represents radius, and we use it often enough. Okay. So we're going to take our dv and change that into this hideous expression and start combining stuff together. So that becomes, instead of now single integral, this becomes triple integral, or the sum of 3 instead of the sum of 1. Integral of rho squared times rho squared is rho to the 4th. Okay. Sine squared phi times sine of phi is sine cubed of phi. d rho, d phi, d theta. Okay. Now, from here, we have to set up our limits of integration, right? This is if we do an indefinite integral, which we could easily do, it would just end up being unpretty. So actually, the limits of integration are rather simple. For rho, we integrate from 0 to r. For phi, we always integrate from 0 to pi. And for theta, we integrate from 0 to 2 pi because theta is the distance around the entire sphere, which is 2 pi. Okay, the angle around the entire sphere, which is 2 pi. Okay. So everybody got it? So I'm going to rewrite this integral with the limits of integration on it, and if you want, you can go back and look at it again. Okay. Let's clear it. So this becomes the integral. Moment of inertia is equal to the integral from 0 to 2 pi, the integral from 0 to pi, the integral from 0 to r of rho to the fourth sine to the cubed of phi, d rho, d phi, d theta. So, of course, to work inside out, we'll start with rho, so because it's a very simple integral. So, anything that is not rho goes to the outside of the integral. So, this whole mess comes to the outside of it, and we integrate rho, which will be rather simple. Okay. So we have I equals the integral from 0 to 2 pi, integral from 0 to pi, sine to the third of phi, times the integral 0 to r. Before I actually do any integrations, make sure the algebra is set up. Rho, d rho, d phi, d theta. Okay. So we're going to work with here. I'm going to work on this integral right here, and we'll come back to the phis later because phis on the outside. So the integral of this is going to be r rho to the 5 over 5, rho to the power over 5. So it's a very simple integral, and I'm showing you a lot more work than necessary, of course. So that integral, 0 to 2 pi, 0 to pi, sine cubed of phi, and then we'll take that integral, which is rho to the 5 over 5, from 0 to r. Okay, which is going to simply be, and then on the outside here we have d phi, d theta. Okay, so that integral from 0 to r is just r to the 5th. Okay, and we plug in r into that equation. So it's not, since r will not be in any of our integrals at all, it goes to the outside of the entire sum. So it's going to look something like this. Okay. Alright, let's clear it. Again, if you need to stop and look at it, please come back and look at it. Okay. So we have, different color. So r to the 5 over 5, I equals the integral of r to the 5 over 5, the integral from 0 to 2 pi, integral 0 to pi of sine to the 3 phi d phi theta. Okay, so that's all we did. So we integrated plugged in R, and that gets R to the 5 over 5. Now, for this piece here, of course, what we need to do from here, integrating this sine cubed of phi, which I already know that integral off the top of my head, but since you guys probably forgotten everything from Calculus 1, let's quickly remind you of how to do that. Okay? So, let's do the algebra here. Oops. So we'll drop the integral for a second. Sine of phi, sine cubed of phi is the same thing as sine of phi times sine squared of phi, which is the same thing as sine of phi times 1 minus cosine of phi, the sine squared of phi, like that. Okay. Once we've set up the algebra, we can then use the substitution to do this integral, and we can plug it back in later. So, doing our u substitution here for this integral, we let u equal cosine of phi, du equals negative sine of phi d phi is equal to du divided by negative sine of phi. And if I plug in 0 in pi, I'm going to get 1 and negative 1, right? Because I plug in u of 0, cosine 0 is 1, cosine of pi is negative 1. So, we'll let that here. U of 0 is 1, u of pi is negative 1. Alright? So, and then we're going to use another trick because we will have even function. I will just write it out for you. So this becomes sine of phi times 1 minus u squared times du divided by sine of phi negative. That kills that. So we end up with 1 minus u squared, integral that. Okay, and so this ends up being the integral from positive 1 to negative 1. I'm one step ahead of myself, actually, even though here, this is the integral of 1 to negative 1 of negative, bring out a negative sign, 1 minus u squared du. Okay. And so, we have even function here, because if we plug in negative u, we get the same exactly function. So we're going to do a little bit of trickery here. First, we're going to switch the limits of integration. Then, after that, we will use the even function rule. So this will become positive negative 1 to 1 of 1 minus u squared du. Then this becomes a positive sign because we switched the limits of integration, so that changes the sign. Then, from here, what we have to do is use the even rule of integration, or the symmetry rule. Okay, so that integral, I hope you don't mind if I clear this hideous mess. Okay, then we use the rule of symmetry here. So then the integral from negative 1 to 1 of 1 minus u squared du is the same thing as twice the integral from 0 to 1 of the same integral du. And I'm not even going to bother plugging it in. Alright, so let's do this integral really quickly. U minus u to 3 over 3 from 0 to 1. And if I plug it in, 1 minus 1/3 is 2/3. So this becomes 2 times 1 minus 1/3, which is going to be 2/3 times 2, which is 4/3. Yes, I showed you all that work even though I did not have to. You guys are good mathematicians. So, it's 4/3. That 4/3 is a constant and will come outside of the integral. Okay? Alright, so we already did the second piece of the integration. We don't have to go backwards. Okay? So that 4/3 is a constant, and if you need to, again, look at the work, you can go back. Okay? So let's do the last part of this integral here. So let's set this up. So we have 4/15 r to the 5th times the density of the sphere. Okay, because it was 1/5 here, and then 5 times 3 is 15. 1 times 4 is 4. Okay, the density of the sphere like that. Okay. And lastly, we're doing the last piece of this integral here. And it's the integral from 0 to 2 pi of d theta. That is a very simple integral to do. So this is theta from 0 to 2 pi times the density of the sphere times 4/15 r to the 5th. And so plugging it in to pi, it ends up being 8 pi over 15 times r to the 5th times the density of the sphere. Right. So far, not looking too good. Looks kind of ugly. But now we can simplify it. Okay? We've done all the calculus. We don't have to do any more calculus. So, density of the sphere is related, of course. Density of the sphere is going to be mass divided by volume of the sphere. The volume of the sphere is 4/3 pi r cubed. So, m divided by 4/3 pi r cubed. And if we do all the fancy algebra, I'm just going to go with. So if we do the algebra, becomes mass times 3 pi. Oops, sorry. Not mass times 3 pi. So it becomes mass times 3 over 4 pi r to the 3rd. Like that. So save you all the trouble. So this density of the sphere is 3 mass over 4 pi r cubed. Now that I have that, I can plug it into the equation for my density of my sphere. So it becomes 8 pi 15 r to the 5th multiplied by 3n, not the company, over 4 pi r to the 3rd. That kills that 5 times. That kills that twice. Pi's cancel. Lastly, 3 r's cancel 3 r's, getting 2 r's left over. Now I can write my pretty expression of what the moment of inertia is. So the moment of inertia, after all this work, is 2/5 mr squared. Okay. So with a solid sphere, we talk about that. We have this measurement of the resistance of its rotation of 2/5 mr squared. Okay, what does that mean for us in a practical sense? It means that, recall that the sphere has the smallest area to volume ratio. Okay, it basically means that with the sphere, it will be a little bit easy. It will be easier for it to rotate than the smaller number here. It will win. It will win in the race, but it will win the race between different objects, and we'll talk about that later. But I wanted to show you how to derive this sphere, and if there are any questions, of course, you may feel free to ask them in the comment box, or you may feel free to bring them up during class, and we'll talk about that later.